So let's say we want a more quantitative way of determining the effective nuclear charge between the nucleus and an electron. So we can use what's called Slater's rules, where we're going to calculate the effective nuclear charge ZF from taking the charge, the expected charge for the atom at the nucleus, Z, and subtracting out a shielding constant, okay, depending on where that electron is. And so to calculate S, to do this calculation, what we need to do is follow these rules that are shown here in the slide. So the first one is we're going to write the electron configuration with this arrangement, okay? And so as an example, what we're going to use is we're going to use vanadium. And so vanadium has an atomic number of 23, okay? And it has an electron configuration, so atomic vanadium with a neutral charge has electron configuration as follows of 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, 3d3, okay? Or as we discussed before, right, the s electrons, right, as we fill them, that s orbital, 4s orbitals, be slightly lower in energy than the 3d orbitals, okay? But for the effect for this, we're going to rearrange this as it states in the rule number 1, okay? So basically, we're going to group 1s electrons, okay, with parentheses, okay, and each parentheses indicates a group, okay? We're then going to group together the 2s and the 2p electrons, like this, okay? We're going to group together the 3s and the 3p electrons, like this. And then we're going to group together the 3d electrons and the 4s electrons. But what the rules say are that the 3d, right, is going to be first. So we put our 3d3 here and a set of parentheses, and then 4s2 by itself, because there are no p electrons, valence electrons, in this electron configuration, okay? All right, so now that we've done this, we can then start, we can look at number 2. So we're going to pick electron to calculate the shielding for us. So let's say we want to determine the Z effective for a 3D electron, right? So I'm going to wear this electron here, okay? And so what we're going to do is we're going to add 0 to S for all electrons in higher groups. So 4s is going to be a higher group. So we're going to take those 2 electrons in there and multiply them by 0, okay? Now, for each electron, so for rule number 3, for each electron in the same group, add 0.35 to S, okay? And so, reminder, what we're calculating here is S right now. So let me back this up. So 2 times 0, right, plus, right, we're looking at the shielding of an electron in the 3D orbital. And so there are 2 other electrons within this group, okay? So we're going to add 2 times 0.35 to the shielding constant, okay? The next rule says, then depends on whether we're using an S or a P electron or a D or an F electron. We're doing a D electron, so we're going to look at 4B. And so this says add 1 to S for each electron in a lower group, okay? So our lower groups are here, here, and here, okay? And so within this group, there's 8. In this group, there's another 8. In this group, there are 2, for a total of 18 electrons. So we're going to add 18 times 1.0, right, for each of those electrons. And that's going to give us a shielding constant of 0. It's going to be 2 times 0.35 is going to be 0.70 plus 18. Oops, you can't see that. Let me move that down. Equals 0.70 plus 18 equals 18.7 for the shielding. All right. Yep, okay. And then, to calculate Z effective on this d electron, we then plug into this equation here, where Z effective is equal to Z. And so again, we said that Z is going to be equal to 23 minus 18.7. And so that's going to give us an effective nuclear charge of 4.3. All right. So on your own, try to calculate the Z effective of for an electron in a 4s orbital. Okay. If you do that calculation, so this is Z effective for a 3D. Okay. On your own, try to do it for a 4s, and so you have the answer on you. What you'll find is that for a 4s, this will come out to 19.7. Whoops, sorry. S for a 4s will come out to 19.7 in vanadium. And so the Z effective will be equal to, again, 23 minus 19.7, and that'll equal 3.3. And so what you'll see then, right, is that the effective nuclear charge on a 3D electron is going to be higher than the effective nuclear charge on a 4s electron in vanadium.